Okay, so my talk is the Spacetime as potential via Clifford algebras. And I first came across Clifford algebras during my PhD, and shortly afterwards I read David Bohm's book on the implicit order, where he mentions how you need an algebra to describe fundamental physical processes. And I then read some of Basil's papers and began to explore the ideas he was pursuing. And I was a great privilege to be able to speak to Basil here in the past couple of years. Yeah, and this talk is a continuation of the program that I think Lyndon discussed about trying to find a geometric interpretation of quantum potential and of the Bohmian approach to quantum mechanics. So, I'm going to start off with a bit of motivation philosophically. I'm then going to give a brief overview of the geometric versions of Clifford algebras, which we've heard a bit about from Hamish and Getty. And then I'm going to discuss how you can start to give the phase space structure by putting a kind of Keeler structure on top of the basic objects. Okay, so start off with this thing.
You've got to do them down. Yeah.
So, there we heard from Tromo's papers. He talked about how in the dynamic universe approach, space-time functions at a kind of potential in the Aristotelian sense, and that's going to be the starting point for this talk. So, potential, like potentia, is the possibilities for future action that kind of encode it into the form of an object. So, it's kind of similar to dispositions or passive causal powers in the more common analytical philosophy, but it's different in that it's more of an innate feature rather than a kind of a secondary aspect. Again, this is a good discussion of some of the ideas. So we heard about how the quantum potential is a kind of active information which informs the quantum state. And in the scholastic or Aristotelian approach, then it is the form of an object which determines its potential, as in kind of a dual sense. What a thing can do is a dual of what it is. Okay. So, interestingly, Heisenberg picked up on this bit and said that the wave function is a bit like the Aristotelian potential. So, with a quote there. And I don't think Heisenberg was an Aristotelian, he's just drawing the analogy in his philosophy of physics. Someone who definitely is an Aristotelian who picks up on this is Wolfgang Smith, who's got a very interesting book called The Quantum Enigma about all this stuff. I think I would be more some kind of Christian Platonist rather than Aristotelian, but I'm still inclined to think that this is a good way to think about what the wave function actually is. So it's sort of the possibility that under a certain interaction with a system, you will get a certain result. It's not identical to the potentia because it's kind of subjective to a particular observer, but it's a very, very similar concept. And that's the angle I'm going to be looking at when exploring the wave function and phase space and Clifford algebras. So the idea is that information determines the wave function, and this is a bit like how the form of a substance determines its potential. Right. So we can use Clifford algebra to represent spacetime. I'll explain how to do this in the next section. It's been talked about a bit by Hamish. And okay, so that's the spacetime side. What about the quantum mechanics side? Well, I think Robert Callahan, who and standing over there, and Basil showed that you can encode the same information in the usual Schrödinger wave function into Clifford algebra, at least for the Schrödinger and Pauli cases, and I think also for the Dirac matrix as well in a second paper. So this builds on work that was done by Basil in the 80s with Frescura. So the picture that we're getting is that Clifford algebras contain the same information as a wave function and can also represent spacetime. So does that mean we can think of spacetime as some kind of wave function? Okay. So we're now going to go on to geometric algebra. These are some useful sources, I think, for this. One of these is not like the others, and that's one there. This is a thing called Clifford analysis, which is not strictly speaking a form of geometric algebra, but is another new technique on Clifford algebras. It's kind of a higher dimensional version of complex analysis, which is something that I will be briefly referring to a bit later in this talk. Okay, so the way I see Clifford algebras is a higher dimensional generalization of complex numbers. So if I look at the real plane and the complex plane, these, I think, kind of look pretty much the same. The difference is I can add vectors on both the real and the complex plane, but I can't multiply two real vectors together. I mean, if I draw this and then this, I mean, what is this multiplied by that? And it doesn't make much sense.
Can I have 1 minute? Sorry,
Yes.
Calum, to interrupt you. The coffee is going to disappear, and it's been taken away. So anybody has an urgent need of a coffee or a cup of tea, help yourself. Otherwise, it will become sorry.
So this is the reason why the square root of -1 is I, because we have angle pi over 2 here, and if I have a vector of length 1 here, I define multiplication so that I multiply the angles. So if I have rho 1 e to the I theta 1 and rho 2 e to the I theta 2, then the multiplication is rho 1 rho 2 e to the I theta 1 plus theta 2. So I'm adding the angles and multiplying the lengths. So if I have a unit vector along the y-axis, and I square it, then I will multiply the lengths, which will get me another vector of length 1, and I will add the angles, and that will give me an angle of pi. So you see the point here, -1 on the x-axis, is the square of the unit 1 of the y-axis. So this is a product on vectors defined in 2 dimensions, and I can repeat this process in any number of dimensions, and this to me is the best way of thinking about what the geometric form of a Clifford algebra is. And if I multiply together 2 vectors, I get a bivector. If I multiply together 3 vectors, I get a trivector, which is the volume, and so on and so forth.
If you multiply together 2 orthogonal vectors, you get a bivector. Yeah, if you multiply together 2 arbitrary vectors, you get
No, in general, you can get a combination of scaling. So you'll get both. So yeah, if I multiply, in general, if 2 vectors are in the same direction, I will get some scalar which depends on the metric. So you see that x multiplied by x is just going to be whatever g is in the x direction, but x, y is going to be like a unit vector in the xy plane. Okay, and so we got particular bookkeeping. We call the number of dimensions in an object its grade. So a volume is grade 3, space-time would be grade 4, a vector is grade 1. If I multiply together 2 objects' blades of the lowest grade object I can form has grade I minus j, and that is called the dot product. The highest grade object I can form is called the wedge product, and that has grade I plus j. So I multiply together a plane and a line. The highest grade of that I can get is 3-dimensional. It's a plane, because if I've got the plane here and then a line here, the best I can do the trivector. The smallest thing I can get, the line, if one of these is in the same direction, if I dot a line into the plane, I will get the vector orthogonal to that line. Okay, so some other useful things. There's a lot of useful stuff going on with duals, and this will be important later. So if I have a box like this in 3 dimensions, I can think of the x and y direction and the z direction as dual. This is like the elliptic duals that you mentioned, in the sense that the z direction fills the missing bit of space that the x and y directions don't. And this idea of complementary or dual subspaces of space is going to be very important in the constructive part of this talk. Okay, so again, there's some machinery there, and there's 2 different sorts of dual objects we can define. In the case of the scalar case, we can define an inverse such that A inverse A equals 1, and we can define an adjoint which satisfies A inverse A is mod A. Geometrically, the adjoint gives the opposite rotation, but the same dilation, and an inverse gives the opposite rotation and an inverse dilation. Similarly, when we are defining these geometric duals, we have the geometric inverse or complement, which is just the missing bit of the space. And we also have the Hodge dual, which is the object in the other part of the space with the same magnitude. And to clarify the difference, if I want to define a box of volume 1, and suppose I have a 1-dimensional square, sorry, a square of size 2, the geometric inverse is going to be a line in the z direction of size 1/2, because it's the thing I have to add to this to get the box of volume 1. The Hodge dual is going to be a line of size 2, because it's the object with the same size in the other dimensions. So, okay, and with this definition, we've got this. The inner product of A and B times the volume is equal to the wedge product of A and its Hodge dual, which may look familiar from if anyone has come across Taylor structure. Okay. And final bit of construction. Well, we have a vector derivative or Dirac operator, which is defined in the usual way. It's the vector, each vector multiplying the derivative in that direction. Interestingly, in 2 dimensions, this gives you the Cauchy-Riemann equations, which is where this Clifford analysis comes in. So there's a very strong link between this and complex analysis. You might wonder, does this generalize? And the answer is yes. It turns out you can extend the concept of holomorphic functions to any number of dimensions using these techniques, where they're called monogenic functions. You even get a version of the Cauchy theorem in any number of dimensions. And it turns out you get a nice way you can treat this thing here as being a Green's function. So you get a nice unification between complex analysis and other aspects of the differential equations and things like that. So there's some quite powerful techniques going on here. This, I think, supports the idea that Clifford algebras should be viewed as a higher dimensional version of complex analysis. So not only do you have this geometrical interpretation, you have the analytical Hartlett-based linkage going on as well. Okay, so what about spacetime? Well, spacetime is represented by this Clifford algebra here. And it contains 1 scalar. It contains 4 coordinate directions, time x, y, and z. It contains 6 bivectors, 3 space-like bivectors, which are going to go like gamma ij, so gamma 2, 3, whatever, and 3 time-like bivectors, gamma 0, I. It's going to have 4 volumes which are going to be dual to the directions. For example, the dual of the time direction is the spatial volume, E1, E2, E3. And we've got the pseudoscalar, which represents the whole four-dimensional volume. Okay, so what's interesting is, it was shown about 20 years ago, this is isomorphic as an algebra to something called the stabilized Poincare-Heisenberg algebra, which is this thing here. And we can note what's going on here is this bit here is Poincare's algebra, which is on the bivectors, which kind of makes sense. The bivectors are rotations or generate rotations. So they basically amplify the events algebra.
So what is it? Is eta just the cross connection?
It is, yes, it is, yeah. I think in theory you could place it with Euclidean metric, but you can get it can get
And ABCD are four dimensions.
yes,
So
yeah. This bit here is a Heisenberg algebra. So the positions and the volumes sort of work like Heisenberg algebra if you assume that I is the pseudoscalar or the total volume. Yes.
wondering, is this the Heisenberg algebra, which I remember reading from some highly paper with he did something to get the extended Heisenberg algebra, and it was then the minimal left ideals of that were the wave functions of his formulation.
So it should be the same Heisenberg algebra. I'm still working through his stuff on minimal left ideas, so that's going to be the next step after this talk. The rest of it just tells you how all of these things interact. So basically, the momenta and the position transform sensibly on the rotations, and you get some fairly sensible computation relations here as well. Okay, so what's interesting here, I think, is what's interesting here is that this shows that space-time has a phase space structure, because I can treat the positions and the three volumes as positions and momenta. One of Basil's searches was to try and find a quantum phase space. So a sort of phase space, a geometrical phase space where the quantum field lives. And I think this suggests it's possible that Minkowski space itself, which has the structure of a phase space, and in a Clifford algebra, so also carries the same information as wave functions, might be the quantum phase space that Basil was looking for. So
What is that R here?
so the R is a constant you put in to make it work dimensionally. So some people try and tie it to things like the radius of the universe. So this is the guy who introduced it, a Portuguese chap called Mendes. He points out it's come up in a large number of places. So it was first written down by a chap called Yang in 1947, and then picked up again by another chap called Snyder in like 49, I think. And their insight was you can try and do quantum gravity by making your space-time coordinates anti-commute to produce the event generators. Okay. So the same algebra appears again in a paper by Lee Smolin and Krasny Wickman, and they have a long discussion as to what constants mean. So they very much want the constants to mean the radius of the universe and stuff like that. And this is the paper that proves that it's the same thing as the space-time algebra, or the Clifford algebra to become a one. Okay, so this is kind of the motivation. We can possibly treat space-time as a phase space using this algebra, and it also carries the same information as the wave function, so is it a kind of quantum phase space? And the answer is it's a work in progress, but there's good signs it might actually work. So first thing is, phase space relies on this idea of Kähler structure. So I have two duals on a manifold. I can define a dual via the metric, which is sort of the vector which will multiply with my vector to give me the norm. And I can define the dual using an antisymmetric form, which is just the Hodge dual I was talking about earlier. It's the bit vector, it's the object in the other, it's the other part of the space with the dual number of dimensions, but nevertheless has the same magnitude. And the Hodge dual said that these two notions of dual are linked, or rather, the Calum structure says that the Hodge dual is linked to the metric dual via this relationship, where J is some kind of, is called a complex structure, and I require that J squared is equal to -1. So the first thing I'm assuming is that this is sort of the Hodge duality on the Clifford algebra is kind of like a higher dimensional version of the Calum structure. So we have the same metric. The antisymmetric form on the in the Calum case, I think, is replaced by the outer product in the Clifford algebra, and the complex structure here, J, is replaced by the Hodge star. And the motivation for this is that the Calum structure is defined only for complex manifolds. So if the Clifford algebra is a higher dimensional version of a complex manifold, it makes sense that you might get some generalized version of the complex Calum structure. And if you're going to do that, this looks very, very similar. It's not totally identical. So in the complex case, J squared is always -1. In the Calum case, double Hodge star is -1 kn minus k, at least in the Euclidean case. So it's only sometimes positive and sometimes negative. But it does perform the exact same geometrical role. It relates the metric inverse to the antisymmetric or symplectic inverse in the exact same way. And it also imposes orthogonality on the two inverses. The J does a complex rotation of by pi/4, which implements orthogonality between V and JV. Equally, B and star V are orthogonal within the space of geometric duals. So this is explained. So there's a very nice paper about duality in Grassmann by Dionot for the tragedy of Grassmann. Okay, so sorry for a bit. That one way again. So this means we can decompose. We can try to decompose the Clifford algebra into complementary subspaces with k and n minus k dimensional subspaces. So in 3 dimensions, lines and planes are complementary. In 4 dimensions, lines and 3 volumes are complementary, and the central bivector part splits into 2. So the time-like bivectors behave like mentor, and the space-like bivectors behave like position, if you're assuming this analogy holds. And there's some ideas similar to this in one of Hiley's papers with Maurice Vigosson and Eric Binns. Okay, so we're trying to treat the dual geometrical spaces as position and momentum. So can we try and put some dynamics on this? Well, this is what I've got so far. Yeah, so for the spacetime algebra, we can try treating position as the vectors and its associated momentum are the 3 volumes. And again, we can look at the time-like and the space-like bivectors as another head. I'm going to work in the Euclidean case, so putting the eta AB to being just Euclidean to avoid issues with Lorentz invariants and Hamiltonians. I think you can get around them, but you have to use Dirac's constrained Hamiltonian or similar methods, and that's a bit more complicated than I can deal with at this particular stage. So, going back to our algebra, we have P wedge x is equal to h bar eta AB I, and this implies that the volume should have units of energy, because h bar is energy. If I think about this as being a metric, it also implies that P is a sort of Hodge dual of x. So P is by x, a dagger. Okay, so I'm going to assume that my volume should be the Hamiltonian times the scalar, because the Hamiltonian should be there somewhere, and it's got the right units. And I'm now going to define a position, the Dirac operator, which is the position vector multiplied by d by the position. And I'm going to define a momentum Dirac operator, which is momentum vector d by d momentum. Okay, and I actually get Hamilton's equations. So if I dt by hi is equal to x naught after a lot of calculation. And equally minus the x for hi is equal to, well, minus 1 to the n p dot. This isn't quite right because I want dx h to be minus dx h to be p. But it does work when n is even, which, given that all phase space is even dimensional, I'm not too unhappy about because there's no reason it should work when n is odd. Right, so in the even dimensional case, this gives you 100 equations. Okay, so far I've only looked at the position and the mentor, the vectors and the trivectors. What happens if I try to generalize this? Well, if I go to a general Clifford algebra, I assume that my position is going to be grade k, and therefore the momentum is the remaining n minus k dimensions. If I run this through again, this dp for h works, I get q dot, but now something odd happens with the q dot h. So I get a -1, and I get this factor 1 plus kn minus k. And it turns out what happens is, this is what I want when k is odd and n is even. It's minus p otherwise. So this is a little bit strange. It's something I want to investigate further. So for odd dimensional spaces, this behaves like you want. For even dimensional spaces, there's a minus sign, which is different to the standard fermionic case. Now, I'm going to suggest why this might involve some more interesting underlying behavior in the next slide. If I look at the Poisson brackets, then these also behave pretty much like you want them to behave, except that I get -1 to the kn minus k here, which is the same factor that I got in the previous slide, making this not equal to the -1 I want it to be. Okay. And what is very interesting here is this side is the same as you get when you try and apply this to Grassmann variables. So if you do Hamilton mechanics and Grassmann variables, you get -1 to the product of the grades here. If they are both even grades, you get +1. If they're both odd grades, you get -1. If they're a mixture, you get +1. And this looks like very similar behavior to what I'm getting in this case here. So it's possible somehow that the even dimensional subspaces correspond to Grassmann variables in some sense, whereas the odd dimensional subspaces correspond to fermionic variables. But this is all something that needs a lot more work, which is, this is the work in progress, but I think there's something interesting going on here. Okay, so this is my conclusions and further work. So the basic idea here is that with the work of Callahan and Hiley, it seems like Clifford algebras can be seen as defining wave functions. We also know from the work of David Hestonese with his geometric algebra that Clifford algebras can represent geometrical spaces. So can we think of a space as a quantum object by kind of mashing them together? Well, it looks like we can, because we can define a Hamiltonian or Kähler-like structure on a Clifford algebra, which means in theory we could put a phase space structure on it. There's a couple of bits of interesting behavior to iron out, like the sign behavior, but nothing which is, I think, physically implausible or which doesn't have parallels in other parts of physics. So in terms of what to do next, well, definitely need to look at the relativistic version. I've just been looking at Euclidean metric, but Spacetime does not have Euclidean metric. This might need some more advanced machinery, but let's see. Second thing is, I'm doing this in the differential forms. So I'm doing this in the Hamiltonian mechanics picture. There are many more sophisticated ways of doing this with differential forms and symplectic mechanics. So, for example, I can define a volume form. So in the usual version, this is the two forms. This should probably now be a pseudoscalar, dp wedge dq, where I define, for example, my dq as a Clifford element is going to be my one form multiplying the dual, the adjoint of the k-dimensional basic element. And similarly, my dp is going to be it's going to be something like EKI dual then dp. Anyway, you sum over all of these, you'll get a pseudoscalar valued form. I'm working on this at the moment, so this will be much nicer in terms of maths. So another major problem is I've been working with orthonormal bases here, and what would be amazing would be to link this to the Einstein equation somehow, because Hamiltonian gravity is quite a serious, it's quite a difficult thing to do. And if you could somehow link this to gravity, it would be very, very nice. What's especially nice is that this implies that the overall volume is conserved, because that's Hamiltonian, energy is conserved. And the total volume is the Ricci scalar. The Ricci scalar being conserved is the vacuum Einstein sort of equations. And what's even more interesting is that if you have both Kähler structure and a zero Ricci scalar, you have a thing called a Calabi-Yau manifold, which pops up all over the place in sort of physics. So again, if there's a lot of ifs here, but if you could look at a non-orthonormal basis and work out how to define coordinate changes, so using the Witt point transformations and Eric Lindzen stuff would be useful here, that you could try and link it to gravity, and that would be extremely useful. And finally, you need to, I think Attel was very interested in the Moyle and Grunwald formulation of quantum phase space. So making some links to that is interesting to see how it compares to Attel's work in that particular area. Right, so almost as the final, the thing that's bugging me at the moment, I can't quite figure out if there's anyone who knows about Clifford algebras or differential form can help with that. I would be very grateful. So there's this formula which you have this dot product of the vector derivative of a multivector, and the way most books say it's equal to the Hodge dual of the outer product of the Hodge dual of the vector. And this is coming from the fact that in Hodge theory, the co-derivative is defined as being Hodge star of the exterior derivative of the Hodge star. Now, it seems to me that this is only going to be true if I can somehow pull the pseudoscalar or the volume form out of the derivative. But this is only going to be true if the pseudoscalar is invariant under the action of my Dirac delta. So it seems to me I'm possibly being very silly here. So please, this is why I'm putting the question here. And I think this only works if either I have an orthonormal basis, so there's no change, there's no Aristotle symbol stuff going on, or if I've chosen a metric compatible covariant derivative, which then just deletes all of the change in the basis directions. But all the books simply say, all the textbooks on this simply say that this is true for any ordinate choice. So I don't know if I'm missing something important, or if implicitly most of the references are just assuming an orthonormal basis. So if anyone gets any help, that would be gratefully received. Anyway, that's the end of the talk. So.
So I'm just trying to understand something. So you're say a volume and a line will be now non-commuting things, right?
The commutation is they might commute. The commutation is each time you swap two orthogonal directions, you get the minus sign.
Okay.
So like EI, EJ, EK is EK, EI, EJ. There's something from identical thing that.
Right. So generally global, generally like the kind of transformation, the point here is a global everywhere.
Yeah.
But you would probably like to do locally, right? Generally covariant.
Absolutely. Absolutely. This is very early days. So yeah, that would probably fall under this thing. Looking at symplectic manifolds, so how I can gauge work with it.
Yeah, that's definitely.
For testing the
Anybody else?
Well, coming on.
what kind of
Well, coming on from that, I never actually read Robert Callahan's book. You said they had a formulation of the Schrödinger equation in Clifford algebra. Doesn't that mean that they must have fields which vary spatially? Does that mean that? No.
So I think yes. I think there's intrinsically a flat background. I mean, I presume you might know better. If you but yeah, flat background. So, but the components of like Schrödinger equation is defined in a two-dimensional sphere with E naught and E dot, and you've got like G naught, E naught plus G1, E1, and then I think the Schrödinger equation is hidden in components of what like G naught is equals. Is it phi plus phi star or something? Or am I getting that mixed up?
Yeah, E to the one plus D1 is 5.
Okay. Okay, so it's going to be 1. Right. Okay. Yeah. So basically, it's hidden in the components.
Thank you.
I used to have kind of discussions, thank you, with Dazzle about the idea of the left ideal.
Yes.
And Dazzle kind of had it, I found slightly sloppy kind of thing. Oh, it's the wave function. And I'm not very happy with, the wave function reappearing in the algebra. What's your position on that? Because the wave function, you're starting off with your Schrödinger equation. So you're doing the standard quantum mechanics. Aren't you getting a lot of the same problems that you had what one has with standard quantum mechanics on that?
So I think that's a very good question. I think that my understanding is where the wave function comes in, it comes in the components multiplying all that the sizes. So so the idea, so let's see. So if I understand the Basil's point is that if you take the ideals are projection operators. So Basil's point, as I understand it, is if you pick projection operators, by definition, this gives you a quantum state because Clifford algebras are Hilbert spaces, like they're vector space to the critical norm. So once you define so Basil's dealing with ideals. So example of idempotence. And by definition, idempotents are projection operators because for a Clifford algebra, every element is also an operator. So once you define an idempotent, this projects out a certain sum of the Clifford algebra, and what's left is a eigenstate in the exact same way as in the usual quantum mechanics. And the coefficients of the basis elements of the coefficients of that eigenstate are then evolved using Schrödinger's equation, and as I understand it. So you're right. It doesn't necessarily fix the conceptual problem immediately. But my hope is that if you can, by giving a geometric picture to the quantum phase space, you can look at, because in the talk last time there was the distinction between the configuration space and physical space, and what I'm hoping is the quantum phase space kind of functions like configuration space, and if that literally is physical space or space-time, or at least it's at least 4-dimensional. What I'm toying with the idea you can exponentiate to get from the energy space back to the position space, but then you can give a geometric version of the Bohm field that is basically just a field that assigns to each point a probability of finding a particle there. So if in itself it doesn't fix the conceptual problem, I'm hoping it might point towards some ways to do it.
Thank you.
Okay.
Thank you.